My name is Jason King. I'm with IBI. I'm an architect and planner and computational designer. I'm the global lead for our computational design practice. And today I'm going to talk about parametric design in a presentation called A Parametric Process for Place Baking. And that will make sense in a minute, hopefully. And before I begin, I just want to say that if you have any questions or comments, feel free to leave them in the chat. And after the presentation, I'll go through and answer what I can. But I'm going to go ahead and get started on my presentation. So the first thing I want to do is just give a definition for my definition of parametric design. So I'm going to key in on a few words here. The first being customizable. So all of the models that we build are built from the ground up. These aren't things that we pull from a shelf that may or may not address the problem at hand. We really listen to the project needs, the client's needs, and the problems presented in the project to build a model in response to that. And for that reason, I refer to this as a process and not a tool, because it's really something we do throughout the process of the project. And it allows us to efficiently and effectively use a lot of data in order to make evidence-based decisions. And in that definition is the word algorithm. I taught computational design for about 12 years at universities, and as soon as I would say algorithm, I would just see my students like filling out drop cards and thinking they signed up for the wrong class. But an algorithm is just a set of instructions, a way to solve a problem, a set of rules to follow in order to reach some sort of conclusion. And the analogy that I use is that a recipe is an algorithm. So this is the visual algorithm for making sourdough bread. And I think it's apt, especially when we're doing urban design or urban planning algorithms or parametric models, because it's really important in a recipe to know what ingredients go into that recipe. That's going to be the first thing you do. So for bread, it might be flour, salt, water, yeast, all of the things we need in order to make bread. Of equal importance is what do we do with those ingredients? So we need to know that we need to knead, rest, how long does it go in the oven, how hot is the oven, how much of each ingredient. So all of those things, ingredients, and then the steps that we take with those ingredients are important to having a loaf of edible bread, or important to doing the correct modeling for a project. And I'm going to talk about a few of the different recipes that we've made across scales, across sectors in the past couple of years. So the first project I'm going to talk about is a very large land area in North County, San Diego. And this was a land use and transit integration study. And I start with this one both because I'm kind of going to start at large scale and then zoom in. And also that this is like parametric design 101. So we begin by looking at regionally at the trends of each of the different data sets or each of the criteria. So where is their ridership? Where are their employment centers? Where is their developable land? Where are their parking lots? Where is their multifamily and mixed use housing? Where does all that exist in the region? And then importantly, we can layer all of these different data and weight them. So this is really useful when we're meeting with a client and they want to kind of do a sensitivity analysis to see the impact that each individual variable is having on the overall patterns that are emerging. So often we'll sit and say, turn affordable housing all the way up and let's see what impact that has on a model, or turn it all the way down to see the impact of it not being involved, or we'll include equity and do that, or transit ridership, or whatever it is. We can see the impact that one individual variable has on the overall pattern. And in this case, we asked 3 questions. Where are we serving well? Where are we not serving well? And where do we need to serve in the future? So from that, patterns emerged of where we need to focus our efforts, either where we're not serving well or where we need to serve in the future. And then we zoomed in a little bit from the kind of region to an individual city, in this case, Carlsbad. And now we're able to look at more granular levels of data. So the diagram on the left is showing how accessible the city is by different modes of mobility. And what we're doing here is, instead of just drawing a half-mile circle and saying this is the catchment, this is how far someone can get in 15 minutes, we're actually looking at it temporally, using the street network and using topography, but seeing how far one can walk in 10 minutes, how far one can bike in 10 minutes, how far one can e-scooter in 10 minutes, and how far one can e-bike in 10 minutes. And then, of course, the rest is unserved. And we're overlaying different points of interest like affordable housing, tourist destinations, job centers, things like that. And then we can really get an idea of what is accessible from a transit station by different modes and what's not, and see if we have the right accessibility too. So if we have a senior housing center and it's only accessible by e-scooter, maybe that's not the right mode of accessibility. And then what we're doing in the next diagram in the center is looking at if we have transit supportive land uses around these corridors. So we're looking at every parcel within a half mile of these focus corridors and analyzing the land use. And this being North County, San Diego, all that yellow is single family residential. So we may not have the density we need to support high quality transit. So the diagram on the right shows every opportunity parcel in that catchment as well. So we know that we have 150 acres of surface parking. We have almost 2,000 acres of developable land, and we have nearly 2,500 acres of county-owned property. So this allows us to kind of look at multiple scales at once to inform our decision making. This next model I'm going to show you is it's an evolutionary algorithm that I'll talk more about in a second. But this was in response to, I saw the former CEO of Metro, or the transit authority in Los Angeles, speak at a conference, and he said he wanted to electrify the entire bus fleet by 2030. And one of the big undertakings was where to locate the charging infrastructure. And I was kind of writing that recipe in my head as I was listening to him. I know I have all the parcels that Metro owns. I have the bus lines. I have the termini of all the bus lines. So what I did was build an evolutionary solver that goes through every potential iteration of a model. So essentially what this allowed me to do was look at, in an afternoon, 100,000 different options for where we should locate the charging infrastructure in order to minimize deadhead driving system-wide. And what an evolutionary solver does really well is finds coalescence between potentially conflicting variables. So if we wanted to have the shortest driving distance only, the answer would be to use 2,700 different parcels. But it doesn't make sense to build charging infrastructure on 2,700 parcels, and also land is a scarce, valuable resource. So what we want to do is use as little land as possible while getting the minimum driving distance. And an evolutionary solver, again, will go through hundreds of thousands of options in order to find coalescence and find the least amount of land and the shortest driving distances. And in a very short amount of time, I was able to identify the 19 locations that were optimal to build charging infrastructure. And what that means basically is if you add the 20th, you don't get any more efficiency system-wide. So 19 was kind of the number that we had. We're also building models around 15-minute community planning. So we deployed this in 2 cities, both Detroit and Cleveland. And the background to this is that the client owned a lot of land in both of these downtown cores and wanted to see how they could get the best and highest return on the properties they own, but also be a catalyst for growth. So what we did was analyze 10 optimal 15-minute cities and extracted all of the amenities that exist in those. So how many grocery stores, how many restaurants, how many doctor's offices, how many veterinarians, all of those things, how many nightclubs. We extracted those, took the mean from the 10 different cities, and then per capitized them so that we could apply them to other cities. So what we did was apply that to, in this case, the model I'm going to show is Detroit. We could experiment with different population growths, both conservative and aggressive. And once we have that, we know what the projected population is, and then we can analyze what's existing. So how many grocery stores do we have here? And then we can find the delta between what's existing and what's optimal. So that's the first thing. What do we need? Then we analyze every parcel for suitability. So is it vacant? Is it near the client's parcel? Et cetera, et cetera. We have about 20 criteria that define that. Then we put a density multiplier. So it should be less dense on the water, more dense as we gradiate away from the water. And then finally we have parking and open space built into that as well. And then finally we have use distribution. So where should things go? We want grocery stores and schools to be near residential. We may want to cluster together restaurants in order to create an entertainment district. So we have, for every single use, we have these like 10 criteria, and we can weight those, and that will change where things are distributed. And then importantly, the feedback we have, or the output we have, is how much of each thing do we need to build? What goes on every single parcel? So we know that on parcel with parcel number X, we need to build a 10-story building, 3 stories of retail, 5 stories of office, and 5 stories of hotel, whatever that is, right? We have all of that information coming out of the model. And then importantly, we also know the cost to build each building and then the potential revenue from that. So we can calculate ROI, which helped us phase this development. And I'll show a couple of, these are some of this is the output plan for Cleveland. So this is the 15-minute community we're recommending. This is what came from the model. Here's more human scale. So as I said, we included open space in the model as well. So, and we had open space biasing towards the riverfront to create an active pedestrian riverfront. Okay. So getting into more building scale, and in this case, massing, this was for a new building on the campus of University of Ottawa. And this is another evolutionary solver that will max or optimize building footprint. And again, it works really well at finding coalescence and conflicting variables. So the 4 that I've pulled out here, although there were about 12 driving this, are area targets, public space shadowing, facade exposure, and view quality. And you can see for every one of these that we generate, we're getting the attached data and metrics from that. So it's trying to minimize the things it wants to minimize and maximize the things it wants to maximize, and then finding that coalescence I'm talking about. And then if you're creating 200,000 options, you need to have a way to analyze those 200,000 options, so you're not just making more data that you can't do anything with. So this is a web-based tool that we built where we're able to bring those 200,000 options in with the attached data, and then just zoom in on the ranges of each variable that work for us, and that will cull it down from 200,000 to just the 3 or 5 or 6 options that work for us. And this is really, for buildings, this works really, really well because we can actually see the trade-offs we're making. So we can say, okay, if we bring the cost to build in, we can say we're hitting 100% of our targets, but we're 400% over budget. If we're going to come in at budget, we're going to sacrifice view quality down to 70%, public space shadowing at 80%, facade exposure at 90%. We can actually see those trade-offs and see if that makes sense. See if we're willing to take that trade-off in order to come in at budget. And this is another building design project. So the background to this is that in Toronto, where this building is located, you can't add new shadows onto existing parks. So we wanted to build a model that quickly would give us the buildable envelope without adding a single additional shadow to the park. So the building behind here is designed and permitted, but not built yet. So there's a chance it will change. And that was permitted before the shadow policy was enacted. So that could still change. So as you see, as that's updating, our envelope is updating as well to make sure that it doesn't add any shadows onto the park. We're analyzing every shadow cast throughout the year at an hourly interval. And then we're using similar data, basically weather data in this case, to design a performative and aesthetic facade. So making sure that we're not getting heat gain or hot spots, and also getting the aesthetic that we want, all the while using as few unique panels as possible. So we've constrained it in this case to 4, and see if we still get the performance and the aesthetic we're looking for. And then we have all the feedback, like window to wall ratio, all the kind of like the facade things that we need. Those are reported to us in real time as well. And we can look through many options in a short amount of time. And this building is permitted, and here's a in situ rendering. And what I really like about this building is that every move we made was really informed by local context. So everything is like we can point to what the force was that initiated the move. And then another project, and there should be music playing in a second, I hope, is another tower in Toronto. And in this case, this was a collaboration with the artist Pharrell Williams. And Pharrell wanted to be involved in more of a way than just slapping his name on the building or putting a song lyric on the building. We really wanted to see how we could blend the art that Pharrell makes with the architecture that we design. And so we landed on a kind of conceptual driver. We used a quote from Goethe that says, "Architecture is frozen music, and music is liquid architecture." And with that, hopefully you hear music in a second. Hopefully you heard that. It's a Pharrell song called Gust of Wind. And what we did, Pharrell chose the song. We analyzed that song, the waveform of the song, which is just data that we can plot on an XY graph. And then we architecturalized that waveform. So this is kind of this blocky language that we were then able to map onto the facade of the tower. So in a second, you'll see Pharrell's song playing on this massing of the tower. And then our idea was to create a sawtooth balcony pattern that follows the waveform of Pharrell's song. So this is just this mod. We had 3 different modules. We could arrange them so that they followed the waveform as closely as possible. So this is Pharrell's song playing, and then we need to find that moment to freeze the music into architecture. And with Pharrell, we chose the moment that was kind of the most emblematic of the song. And here's the abstraction of Pharrell's music onto the facade of this tower in Toronto. And I show this, a lot of these are tools that we can use in different places. So the 15-minute model, all we do is change the ingredients from Detroit to Cleveland or to Austin or to Salt Lake City and then run the analysis. Something like this is a little more unique, but I show it A, because I think it's cool, and B, because you can use a lot of different data inputs in a parametric model. Anything that can be quantified, and even some things you might not think can be quantified, can go in as a driver or as an ingredient in a parametric model. So a couple more I'll show. We're using this for energy optimization, daylighting and energy optimization. So I'll go through the process of how we do this. First, we start with the basic site geometry. So setbacks, all the things that are going to kind of like drive the massing or form of the project. Then we bring in weather data and material data, put that in the parametric model. Then we're using a lot of stuff from EPA, like different radiance and DaySim software. That then creates a daylight and energy model, gives us visualizations that we're able to re-input to optimize and get feedback, create a feedback loop and optimize the project. So as an example here, you'll see we start with the site boundary, we have the setbacks, that generates buildable form, and then we can run an evolutionary solver to go through many different options. We have all of the material parameters. So what's the R value? What are the glazing parameters? What's the wall makeup? All of that, so we can get as close to accurate as possible here, and then analyze each of the options. As you see here, we calculate the heating load, cooling load, run that through our Design Explorer, where we've generated these several thousand or 100,000 options, and then we're able to just zoom in on the specific ones that meet our criteria. Additionally, we're using these tools to calculate our carbon footprint. So we've developed a dynamic carbon model that we're mostly using in landscape projects at the moment, but we've developed it for architecture as well. And what this allows us to do is see how our material choices affect the carbon footprint of a specific project. So we're able to see in real time what one material versus another, what the impact will be on the overall project. So if we choose stone instead of crushed stone or wood or something, we can see the impact that has. But importantly, we can also look at the sequestration measures to see if we add these types of trees, so large deciduous, large coniferous, what sequestration impacts that's going to have. And then we can see how long it will take our project to be carbon neutral. So this helps inform a lot of the a lot of the material decisions we're making in these types of projects. And then we've got a beta version built for architecture where we can basically calculate the volume of the different materials we're using and get a carbon footprint for those. The difficulty with architecture is that as you change the building form, the structural member size is going to change. So there's a lot of back and forth between like structural engineering and design and then the carbon footprint measuring. So it's a little more of an undertaking than a landscape project, but we're working on that. And then finally, we're doing a lot of modeling around mass timber design and construction. So this model is going to show kind of 3 steps of mass timber thinking. The first is finding opportunities for a mass timber building. There are specific programs that it works better for, and then there's a kind of size that's optimal for mass timber. It's between 6 and 18 stories. So we applied this. So that's the first, is choose the opportunities. The second is to generate the structural system, and we've got a model that will automatically generate a structural system based on basically the footprint of the building and the height. And then finally, facade design and engineering. So you'll see first, this is in Detroit again. We're looking for the best opportunities for our mass timber building. So we're identifying parcels of the best fit. And then we're looking at the structural typology and the massing. And then it's facade designs. And then we're able to evaluate the environmental impact and extract insights and look at this holistically. So you'll see first, we're going to rank every single building that we developed in one of our Detroit models and see which ones are best suited for mass timber. So we're looking for probably office or residential between 6 and 18 stories. We do want a specific area for a site, like there's a kind of minimum site area that we're looking for. So this is the first step. Again, zoning, accessibility, density, parcel size, building height, and then specific programs. So we then find this office development and this residential development. And then we can zoom in on those and get more granular in our design. So the first thing is to design the structural system, and you'll see that the structural system responds to those curves, the footprint, and then any voids in the building. We can adjust the bay size, the spans, all of those, and the sizes automatically update in this as well. So we're able to prototype really, really quickly, and then look at different facade designs, different divisions, how much is opaque versus transparent, all of the things that go into building a mass timber building. And then we can also look at its energy performance and things like that. So as you've seen, we're using these tools across many different sectors, many different scales, but it enables us to really make informed and evidence-based decisions across a wide variety of projects. And I'm happy to take your questions now. Thank you. So looking in the chat. I'm seeing that people weren't seeing the slides now. Please show again at the end of the project, which was about shadow study process effect on the envelope of the building near the park in Toronto. So Saeed, what did you want to know about that project? Okay, I can re-show the Toronto. So this project was just driven by the fact that you can't add new shadows onto existing parks. We built this model that optimized building envelope, and then I think Saeed wanted to see the final. So this is the final rendering of the building that was designed by those local site or informed by those local site forces. I think that's what you're asking, Saeed. Do you use big data for city planning or just the data you retrieve? So yeah, we use a lot of data sources for the city planning we do, and a lot of this is in response to when I start a project or when we start a project with someone like Metro in Los Angeles, we're given a ton of data. And then there's also in the county and city of Los Angeles, there are many, many, many open data sets. And it may be 40 different data sets, each with 200,000 rows of data. And there's just no way for us to use that amount of data if we're using traditional methods, right? Like there's not time or budget in order to address those. And then we end up just relying on bias and intuition. But this way, we're able to let the computer go through those 40 data sets and 200,000 rows and make sense of it. We build in those associations and what we want it to do. And then that informs us as humans to make better decisions when we're doing a planning or a design project. Jason, when you looked at the 15-minute city in Detroit, did you also apply this to suburban communities that surround Detroit? In this case, this was just the CBD. It was the only place that we were working. But we have applied it to more suburban areas in Austin that we're looking at where new train lines are going to see how we could build better communities around future transit in more suburban areas. Can carbon neutrality be modeled at the city level? It could be. It depends on the inputs that we have and then basically how good the data is, right? If we're doing a smaller project with carbon neutrality, we build the borders around where we're looking and we can be a little more sure of the data. When you start to do like urban heat island modeling or large scale carbon modeling, then you're reliant on the quality of your data, and the data that I've seen, like down to the level of like materials in a park, just doesn't exist, and we need that level of granularity in order to do accurate carbon neutrality modeling. So hopefully I didn't skip over any questions, but if anyone else has any questions, I've got a couple more minutes. Sorry about the tech issues. It seems like people were seeing blank screens for a minute. Can you account for soft factors in your modeling? Tim, give me an example. I think I understand the question, but I want to make sure I'm addressing it correctly. Michael, feel free to send me an email. So, Tim, I'll take your question to mean, let's say, non-quantifiable things. And the answer is, yeah, quality of life experience, yep. So we had a big client who I signed an NDA with, but a big search engine who wanted to incorporate happiness into a master plan. And happiness isn't something that a shapefile exists for. You can't go to the in this case, San Jose city open data and download happiness, right? But there's tons of academic research into urban happiness, and there are analogs or indices that you can use analogs and build an index for urban happiness, and then use that, right? All of the things that go into quality of life might be quantifiable, whereas quality of life may not be quantifiable on its own, right? But we have used some of those more soft criteria in analysis before. Do you correlate, crunch the data yourself, or use data set? We use data sets, but that doesn't mean there's a lot of correlation and crunching going into that. And I would say the most time on all of these projects is spent collecting the data and then harmonizing the data. The first project I showed in the NCTD region, there were 7 different cities, which mean we had 7 different data sources, which each of them had their own fields and orders and all of that. And right now we're doing a project where there's 33 unique cities. So it takes time for us to make sure that like zoning aligns across all of the 33 cities, right? They might each have different zoning codes, or even just one of them says C, or one of them says C1 without a dash, and one of them says C-1, right? And we need to go in and harmonize that across the data sets. So that's what takes probably the bulk of the time on most of these projects. How can we blend parametric design with sustainability? I think a lot of that's what we're trying to do. I do a lot of TOD work and transit work, and we've done affordable housing projects where we build in VMT. So we're actually looking at ways to incorporate sustainability and equity just in every project we do. It's not this project is sustainable or this one's not sustainable or this one's equitable and this one's not equitable. We build those into all of the analyses that we do. I mean, and more explicitly, like just making sure that, I mean, the energy modeling I showed you, making sure that buildings are more energy efficient, that's a pretty explicit example, but I do definitely try to build in sustainable at the master planning scale as well. Can models be applied on older buildings and districts or only new builds? Depends on the data. It can be applied as long as the data exists. Anything there's data for, we can apply it. And we actually, on that note, just did some pro bono work for a university in Knoxville, Tennessee, that was very old buildings, but we had the right information about them, or it was a small enough campus that we were able to get that data on our own. Happy to take a couple more questions if you have them. I appreciate everyone's time. If you have any questions or want to talk more about this, I will put my email address in the chat right now. And feel free to send me an email. We can set up a private chat or friend me on LinkedIn or whatever you want to do. But I appreciate you all coming. Thanks for your time.